I use position, velocity, and acceleration to describe linear motion. But if I stand here with my bike wheel, and I rotate it like this, the bike wheel spins around. The bike wheel doesn't go anywhere. It doesn't end up on the other side of the room. We couldn't do an experiment to determine how fast it's going because it's not going. And it also does not have an acceleration. It just sits here. But it is moving, but it's rotational motion, not translational motion. So I can't describe this rotational motion in the context of X and V and A. Instead, I describe it in terms of angular quantities. Now here on the wheel, I have a sticker which describes the position. I just put it here at the top. I can choose to call this 0, the origin, the beginning, the start, because I always get to make that choice. And then if I turn the wheel, the sticker moves, in this case to the right, as the wheel rotates. Here's a diagram that describes this sort of officially, where I have the mass. I'm imagining that this is some kind of mass like a marble, and it's going to move along the arc length, and I can describe how far it goes in terms of S. I can describe how far it goes in terms of S. The distance it travels along the arc. But you see, it's completely equivalent to, say, the angle. If I tell you S, a certain number of meters, then you could look at that circle and say, ah, yes, that's how far it goes along the circumference. But similarly, if I told you the angle, you could just as easily tell the new position of the rotated mass. Now that angle here is represented by the Greek letter theta. When we talked about period and frequency, I already mentioned this angle measure in my arc length formula, which I told you was very important to me, and it's going to make an appearance again in this lesson. The thing was, I don't measure the angle in degrees. My reason for that, which I won't restate in detail, but my fundamental reason for that was, I want the arc length formula to be true. And for the arc length formula to be true, I can't measure angles in degrees, womp womp. I have to measure angles in radian measure. So I'm going to describe the position of a rotating thing, not with an X, but with a theta. When we learned about linear motion, I said positions change. And so I needed a quantity that described the change in position. And that was the displacement. Here, hopefully, very familiar to you, even though it was a while ago. The position changes, so I have a final position and an initial position, and when I subtract, I get the quantity known as the displacement in meters. I'm going to do the same thing for rotational motion, except there's going to be an initial angle, theta naught, which I can choose to call 0 in most cases, and probably will, and a final angle, theta. And if I take theta minus theta naught, I get the angular displacement. Don't let it bother you too much. I had displacement, and now I have the angular version of it. We call this the rotational analog of displacement, is the angular displacement, delta theta, because the angle changes when a thing rotates. Don't overthink it. It's as simple as it seems. Well, you know what comes next. Once I have a displacement, delta x, I realize that those displacements happen in time. And so I create the quantity known as the velocity. Linear motion in a straight line is described by the velocity. You just take the displacement in meters and divide by the time of the displacement in seconds, and you get the velocity in meters per second. That's very familiar. I've done a lot of that. Well, now I'm going to describe rotational motion with the angular velocity, the rotational analog of velocity. Simple. Where I took delta x over t, I'm now going to take delta theta over t. The angular displacement over time is known as the angular velocity. This symbol is the lowercase Greek letter omega. I know it looks like a W, but it's a chubby W. It's specifically drawn this way. The lower Greek letter omega is called the angular velocity. but it's not a vector. When I talked about position, velocity, and acceleration, I harped on the fact that position, velocity, and acceleration were vector quantities. Well, the angular position, the angular displacement, and the angular velocity are not vector quantities. So here I've defined the angular velocity, but I could just as well say angular speed, as I've indicated here in the title. In the case of angular velocity, calling it angular speed is completely equivalent. There's no danger there at all because it's not a vector quantity. So sometimes we say angular velocity, sometimes we say angular speed, and believe it or not, by the time I'm done today, it'll have a third name. But we'll come to that by and by. So now I have angular position, angular displacement, angular velocity. You know what comes next. Angular acceleration. Because velocities can change, I define acceleration as the change in velocity divided by the time in which the velocity changes. The velocity has units of meters per second and time is in seconds. So the units of acceleration are meters per second squared. Rotational motion is described by the angular acceleration, which is given the symbol, the Greek letter alpha. It's a lowercase alpha. The angular acceleration is the change in the angular velocity divided by time. Now, the angular velocity has units of radians per second, and so the angular acceleration has units of radians per second squared. But I previously made an argument that radian is not a unit. It's just a tag that I put on to let you know that I'm using radian measure. So radians per second squared is really just per second squared. That's kind of funny. Per second squared. And so I write it often as seconds to the minus 2. So the units of acceleration, meters per second squared, and the units of angular acceleration per second squared are a little bit different from each other. It takes some getting used to. But since we're going to practice solving some problems, we'll have some opportunity to get accustomed to that. It's easy to switch between the translational quantities and back again, from angular to translational and back again. Here is my arc length formula, very familiar. S is equal to r theta, theta measured in radians. This is position, and this is angular position. So there's velocity, v, and angular velocity, and look how similar the relationship is. The translational speed is equal to r times the angular speed. So it's, in a sense, it's like the arc length formula. You might call it, nobody does, but you might call it the arc velocity formula. You might call it that. Nobody does, but it's sensible. If I have an arc length formula, I now have I could say maybe arc speed formula. That would be another way that I could call it. And the same relationship for the acceleration. The translational acceleration is r times the angular acceleration. Could call that the arc acceleration formula. Nobody calls it that, but you could do, and would make an awful lot of sense. What I've done in each of these three cases is said, give me on the left here, give me theta, I'll tell you what S is. Give me omega, I'll tell you what V is. Give me alpha, I'll tell you what A is. And on this side, tell me what S is, I'll tell you theta. Tell me V, I'll tell you omega. Tell me A, I'll tell you alpha. So I can go back and forth between the translational and the angular quantities. For example, here's my wheel again with the sticker on. Looks like a star. As I spin it around, the sticker has a speed as it goes, a certain number of meters per second as it goes around. And that's perfectly fine. I think you're comfortable with that. It goes at a rate that is the number of meters per second. But if I take that number of meters per second and divide by the radius of the rotational motion, which is from the center of the wheel to the location of the sticker, that would be the radius, then I can describe this as the angular speed. I can describe it either way. Now, as a student of physics, it would be perfectly appropriate for you now to say, why do you give me two ways to do the same thing? Physics is hard enough. without having two ways to describe the same thing. And that's a very fair question to be asking at this point, and I have an answer. It's coming up. Just a few things to clean up first. This little bit of happiness here. In this periodic motion unit of ours, we've discussed period and frequency. And yesterday we talked about circular motion, where an object goes around in a circle, just like the sticker on my wheel there. It goes around a certain distance, which is the circumference of the circle. And it goes around once in the time period, here capital T. And of course, because the time period is 1 over the frequency and the frequency is 1 over the time period, I can also calculate the speed as 2 pi r times the frequency. Well, here's a little bit of algebra. I'll take this r that appears here on the right in 2 pi rf and divide it to the other side of the equation so that v over r is equal to 2 pi times f. Well, v over r is the angular speed. Omega is equal to 2 pi times the frequency. It's hard to express this to you because you have limited experience with physics thus far, but this equation is like the physicist's best friend. It is extremely useful and important to all of our physics, way beyond what we do in this course. Somewhere there's a physicist doing the most important and most innovative physics that there is and relying on omega is equal to 2 pi f to relate the angular velocity, the angular speed, to the frequency. It's a simple relationship. And because of this lovely relationship between omega and f, the angular speed omega is sometimes referred to as angular frequency. In fact, as an experienced physicist, it's a little bit difficult for me to say angular velocity and angular speed because I always call omega angular frequency. I always call it angular frequency. And by the way, it makes an awful lot of sense because omega, the angular speed, has units of radians per second. But radian's not a unit. So the angular speed really has units of per second, which is hertz, which are the units of frequency. So it's not surprising to talk about angular velocity, angular speed, as if it's a frequency, because it has units of frequency. If it walks like a duck and quacks like a duck, then I guess this one's a duck. Why is this a good idea? Well, I've got another case study for you. Why this is a good idea. I am a bit of a cycling enthusiast. I have a problem in my life that I have a number of expensive hobbies, and bike riding is one of them. One of the things that you come to understand when you seriously bike ride is that bike riding is all about cadence. When you practice bike riding because you're going to bike ride competitively or you're going to bike ride for far distance, and the greatest bike ride that I ever had, I rode from my house in Drexel Hill, which is way south of here. I rode from my house to the Cape May Lighthouse in Cape May, New Jersey, which is about 96 miles. I started in the morning and rode 96 miles and only got off the bike twice for flat tires. That is a big bike ride. When you train for something like that, you learn that you have naturally, because of your body and your bones and your muscles and all of your tendons and everything, you have a natural cadence that you pedal at. And for me, it's like built in. This is my pedaling cadence. This is the frequency of my pedaling that I do. But you all know that a lot of bicycles have gears. You can shift gears. When you shift gears, it gets easier to pedal if you shift down, and it gets harder to pedal if you shift up. Well, that's not how it works. When you're cycling, seriously, you want to pedal with your cadence. But now you hit a hill, a downhill, and it's easier to pedal. And so that makes it necessary for you to pedal faster, but you don't want to do that. You want to keep your cadence. So you shift gears. You shift gears not to adjust your speed or to adjust the difficulty of pedaling. You shift gears in order to keep your frequency the same, in order to keep the cadence the same. So you gear up because you're going downhill and it's easier to pedal and you keep your frequency. But then you hit a hill that's uphill and all of a sudden it's harder to pedal and that makes your frequency slow down. You don't want that. So you change gears, you gear down so that you can keep your cadence. Whenever you shift gears, if you keep your frequency of pedaling the same, the speed of the bike changes. Now, if you then say to somebody, I wish I could ride faster, then be stronger. Because you're going to pedal with a particular cadence and shift gears. So the only way to be faster is to be stronger. The bike shown here in the picture is called a fixie. And you often see these, particularly you'll see them at the shore. There are no gears. What you'll notice is very, very common. Perhaps you have your own bicycle at home and you know that this is true. This gear on the back wheel is smaller than the front gear. We call this one the crank and call this one the cassette. Doesn't matter, nomenclature. This front one is larger than the back one and the chain goes around. On a bike that shifts gears, on the back, there are many gears of different ratios, the size of the gears. Look at the back wheel on the bike next time you're in the garage. And the gear on the back has different sizes, different radius. Sometimes the gear on the front, not always, but sometimes the gear on the front. In the case of this bike, there's one gear in the front and one gear in the back. Every point on a gear and every point on the wheel has a different speed. You see the stars going around, it has a particular speed. It has that speed because in a time period, it's got to go all the way around. So there's a certain distance that it has to travel at a particular time. But think about a point that is closer to the center of the axis of the wheel. It goes around once in the same time, but because it's closer to the center of the wheel, it doesn't have to go as far, which means the star here on the outside is moving fast. And any other point towards the center of the wheel is moving slower, which means if you want to describe the rotation of the wheel in terms of its speed, every part of the wheel has a different speed. That's horrible. That makes it very difficult to describe the speed of the wheel when every part of the wheel has a different speed. That is why I want angular quantities. Because while every part of the wheel has a different speed, every part of this wheel has the same angular speed. So I can use omega to describe the rate at which this wheel turns. And when I say there's an omega, I'm talking about the whole wheel. I don't have to worry about the details according to the radius. The whole wheel has the same angular speed. So here's what I can do. Here's my little diagrammatic version. Here's my front sprocket, the one that has the pedals attached to it. And when I do my pedals, I push down, I push down, I push down, and this sprocket turns this way from the effort of my pedaling, pulling the chain over the top. Now at the bottom, I've let the chain appear to be a little slack. On your bicycle, it's a bad idea if this chain is just dangling slack. So there's some nonsense on the back called the derailleur, which takes up the slack of the chain so that you can change gears and the chain stays snug and doesn't pop off. But here, I'm just letting it hang slack and then it goes over this. So my effort to turn this sprocket turns the rear wheel. Here's a fact though. The rate at which the chain comes off the top of this sprocket is equal to the rate at which the chain comes on here. The speed is the same as the speed, but the radii are different. The result is that for the wheel on the left, R1 omega 1, which is equal to the speed, is equal to R2 omega 2, which is equal to the speed. It's the same speed. Since it's the same speed, they're related to each other. I'll simply divide the R2 to the other side of the equation and flip it. So that the angular speed of the rear wheel of the bike is equal to this ratio of the radii of the gears times the angular frequency of the front gear, which is me pedaling. This is my cadence. This angular speed is my personal frequency of pedaling. And it gets multiplied by this ratio, which is called, I know a term you've heard before, the gear ratio. The gear ratio, the radii of the gears. Now, the way that I drew my diagram, R1 is bigger than R2, which means while I'm over here pedaling at my cadence, the back tire is turning at a higher frequency. So the speed of my bike is faster than the speed of my cranking. If both gears were the same radius, then you would have to pedal as fast as the tire was turning. And you're not going to get anywhere. You might as well be running at that point. You don't get the advantage of the bicycle. The advantage of riding a bicycle down the boardwalk at the shore, as opposed to running, lives in the gear ratio. Because changing the gears changes the ratio, and changing the ratio changes the speed at which you ride. Which is, when I was a kid, I don't think they do it anymore, but you used to say a 10-speed bike. That didn't mean that you could ride it only at 10 different speeds. What it meant was there were 10 different gear ratios, and the gear ratios affect the speed.
Mm-hmm.